Hi guys, these are your notes for section 8.5, and today we're going to talk about products with radicals. What we're going to do is we're going to apply the root of a product theorem to rewrite products of roots or to calculate a geometric mean. And here's a journal choice for you. Basically what we're looking at today, is radicals, and this should be reviewed because you can always change a radical to an exponent, and we've done these exponent rules before, but today we're going to kind of try to avoid changing them if we can to an exponent and get more comfortable with the radical notation itself. Okay, so fractional exponents, rational exponents, remind me of the rules, okay? In particular, I do want to talk about multiplying exponents, but let's say that we have x to the 2/3 to the second. Okay, this is power to power. What do? You just multiply the exponents. That's x to the 4/3, right? They do want to talk about the multiplying exponent. So x to the 2/3 times x to the, let's do 4/3 to keep it easy. What do? You're going to add the exponents because they have like bases, right? So it's x to the 6/3, which is x squared. Okay, now if I have x to the 2/3 times x to the 1/2, is this as easy of a problem? No. What makes this more difficult is that I don't have the same denominator in my exponents, so I could change this if I needed to add them, but it becomes a trickier situation when I have x to the 2/3 times x to 1/2 because it would be like plus 1/2. So what do I do here? Well, I could change this to this one. I could change them both, I suppose, so that this common denominator of 6, and I'd have 4/6 plus 3/6, which would be 7/6. But we kind of changed the meaning of what this problem is talking about then, because this x value here could possibly have negative values, and this one could not. Okay, so we were talking about how things change up when you go from these rational exponents, because the denominator mean different things when you take a third root of something and a sixth root of something. So it's something to keep in mind, and it gets a little tricky. Here is the theorem that we're talking about. For any non-negative real numbers, x and y, this one we've seen. Okay, a product of rational exponent, we take it and multiply it through. Pal tribute, if you would. Okay, the same thing is true when you have radical form. The nth root of x times y is the nth root of x times the nth root of y. And this is very, very helpful whenever you are simplifying radicals. Okay, let's look at some examples here. First of all, I always hate how they say without a calculator and they give you such large numbers. The cube root of 320 times the cube root of 25. What they're wanting us to do here, and I don't think everyone would do this in their head without a calculator, is they want you to take that to the cube root of 320 times 25. It is legal for me to put those underneath the radical together because they are both cube roots, because this would be like 320 to the 1/3 and 25 to the 1/3. Okay, this is the same thing as this, but I think where you're confused is we did look at an example. If you remember, we had 5 squared times 2 squared, and I said, can we do this in our head? And we're like 25 times 4, 100. But there's another way we could have done this. Because the exponent is the same here, we can multiply the 5 times 2, which gives me 10 squared. Okay, because that would be the same as 5 times 2 squared, which is 5 squared, 2 squared, power tributing. If the exponent matches up, you can multiply those two numbers together to get like a super base, if you would here. So these are the bases. The exponent's the same, so to get the like base, super base, we would have, that's like Nicki Minaj, that's funny. Okay. I never heard said that before. 320 times 25, that's 8,000, I think. And that would give us, when we take the cube root of that, I get, the cube root of 8 is 2. There's 3 zeros, it's going to be 20. That's how they wanted you to do it without a calculator. but I don't blame you if some of you grabbed a calculator on that. Okay, here we're breaking out that assume that x greater than or equal to 0 thing again, and that's going to show up a lot of times because, like I said, things get a little wishy-washy with radicals because you can't take the square root or an even root of a negative radical. They want us to rewrite using the root of a product theorem. Basically, because we can't do the fifth root of 8, it doesn't help us at all. I get the fifth root of 4x to the 8th. I'm going to work and multiply these together, and I will get 32 x to the 8th times x squared is x to the 10th. This is the same thing. Now I'm going to break it down. I just multiplied it together, but now I'm going to break it down into a way that will help me. So the fifth root of 32 times the fifth root of x to the 10th. Well, what is the fifth root of 32? That's 2. The fifth root of x to the 10th, okay, that's x to the 10th to the 1/5. That's x to the 10 over 5, or x squared. And some kids do need to write this out every time. Others can see right away that I'm going to be dividing these out. Whatever you need to do, do it, but make sure you can get that variable correct. Okay, simplifying radicals. You have done this before, but we dealt mostly with square roots when we did this before, because whenever you did triangles in geometry. Okay, so we're basically going to break this down to things that will be easy. 125 is easy because the cube root of 125 is 5. Cube root of a to the 12. I'm not going to leave it as a to the 12. I guess I am going to leave it to a to the 12 because 12 divided by 3 is 4. This isn't the example I thought it was. And I'll have cube root of b to the 27th. The cube root of 125 we said is 5. I'm going to write it over here. The cube root of a to the 12th is a to the 4th because that's 12 over 3. Okay, and b to the 27 over 3, that's b to the 9th. So when I simplify this radical, I get 5, a to the 4th, b to the 9th. Okay, this is the stuff I thought we were talking about. Okay, who remembers how to simplify radicals? We're going back to geometry here. If I have the square root of 100x squared, you guys are like, oh, this is so easy. I remember square root of 100 is 10, square root of x squared is x. Okay, great. But it gets a little trickier when I have the square root of 200 x to the 3rd. What makes this trickier is that 200 is not a perfect square, so I need to break it down and change it to a product of something that is a perfect squared, like 100. So we're going to change this to 100 times 2. X to the 3rd also is not a perfect square, but it can be composed of x squared times x. Now I can break this down to lots of little roots. Square root of 100 times square root of 2. And I usually only write this step that I'm writing now when I'm explaining this for the first couple times. This will be a step you guys will eventually kind of drop out. So it's going to be 10 times square root of 2 times x times square root of x. Let's make this look nicer. Put the 10 and the x together, and that will be out front. 10x square root of what's left underneath? 2x. That is how that simplifies. So what is the procedure when we do this? Well, basically, you're going to make a perfect list, and it was very easy to find 100 that went into here, but sometimes you deal with numbers that you don't know what number goes into it, so you kind of have to guess and check all those perfect squares. So sometimes it's nice to have a perfect square list handy. It wouldn't be too handy today because we're not just going to be dealing with square roots, but we're going to be dealing with cube roots as well. When you're, 7 squared, I said cube root. When you're dealing with, if this said the cube root of 100, then you would need a perfect cubed list. 1/3 is 1, 2 cubed is 8, 3 cubed is 27, and then these are the numbers you're going to try to break down that base to. We're going to have lots of examples, okay? When you have variables with exponents, you're going to change that exponent to multiples of the root. Here it was a square root, so I needed an x squared there so I could take something out. If it was a cube root, I'd want a multiple of 3 in there. Okay, like I said, we're going to go over lots of examples. Hopefully this makes sense, and if not, you need to jot down some questions so that we can ask. Okay, the 5th root of 96y to the 11th. Okay, we're going to break this down. Because it's a 5th root, we need a perfect 5th fifth list, and we won't have to go very far because 96 is not that big of a number when talking about things to the fifth power. I think that's what we need here is 32. So we're going to change this to the fifth root of 32 times 3. What am I going to change y to the 11th to? Well, I need it to be a multiple of 5. So I'm going to change that to y to the 10th, which is a multiple of 5, times y. Okay, here's how I usually do it. Back here I wrote each one as a separate radical. Usually what I do is I circle the things I can take out. Fifth root of 32, I can take you out. Fifth root of y to the 10th, I can take you out. What is the fifth root of 32? Well, that's 2. What is the fifth root of y to the 10th? That's y squared, because that's 10 over 5, which is 2. What's left underneath that radical? It is a fifth root. Don't lose your root value here. 3y is still underneath, and that cannot be simplified. So this is how we can rewrite the fifth root of 96, y to the 11th, with a smaller power of y. Okay, I hope that makes sense. We're going to look at some more of these. Find E and F. Okay, so I got the square root of 600. What am I going to break this down to that's smaller? Well, what times 6 is 600? E has to be 100, because I'm going to change it to the square root of 100 times the square root of 6. And what is the square root of 100? That's going to be 10 root 6. Okay, the cube root is 1600. What am I going to change that to? Well, I wish I grabbed my calculator here. Okay, the cube root is 1600. They're going to change that to, well, 1600 divided by 25 is 64. So they're changing it to the cube root of 64 times the cube root of 25. Why would they pick that number? Why did they choose that factoring combination? Because they made a perfect cubeless. And 8 does go into 1600, but it's not going to be the biggest thing that goes into 1600. So since 1600 is a little larger, we're going to take our list a little further to see if any other numbers go into it. And that's where they got 64. Okay, so they take it to 64 times 25. The cube root of 64 is what? 4. So that's 64. That's 4. Okay, let's try 96. Identify the expression that is not equivalent to the given. Okay, well, 48 times 2 is 96, right? Cube root. This will work out. This one's okay. 12 times 8 is also 96. Cube root. That one's okay. 8 is on the outside. If 8 was to be on the inside, we would have had to take 8 cubed, because this would be the same thing as the cube root of 8 cubed. That's how they got 8. 8 to the third power is 512. So then that would be the cube root of 512. 512 times 12 is way bigger than 96. C does not work. For 2 to be on the inside, it would be the cube root of 2 to the third. That's how they got 2, because those things kind of canceled out. That would be the cube root of 8. 8 times 12 is 96, so that one's okay. 16 times 6 is 96, so that one's okay. And 24 times 4 is 96. So I think we found our answer here is C. Okay, these are fourth roots. I don't know if you can read it. It's a little small. 5 times 250. I'm just going to jot down what we also have here. This is the fourth root of 1250 by multiplying those together. So I know D is going to be okay here. Okay, 50 times 25. I'm going to do the ones that are easier to check first. That's 1250. So this one's also okay. 5 to the fourth times 2. 1250. This one's okay. And 125 times 2 times 5. 1250. This one's okay. Okay? So these ones are the ones that are okay. Now let's look at these more tricky ones. We're going with fourth root. So for this 2 to have happened, it would have been the fourth root of 2 to the fourth. 2 to the fourth is 16. 16 times 5 is 80. Not big enough. B does not work. Would this one have worked? The fourth root of 5 to the fourth. 5 to the fourth is 625 times 2 is 1250, so that one is okay. I hope this is making sense. Oh, I don't want that to happen. Okay. How about this one? 128y the 14th. I can't even tell what it says. I'm guessing a 6. Let's go with a 6. Okay. 128 y 12 y squared 2 plus 12 is 14. This one is okay. Let's try 6, 12, 13, 14. The variables are okay. 2 to the 6 times 2, 128. B is okay. Great. I got the scribbly line thing going on here. 2 to the 7th, 128, y the 14th. This one is okay. And last one is 128, y the 14th. This one's okay. Okay, so let's now try these trickier ones. I can tell right away which one's not going to work. This 64, if I put this inside, it's going to get way too big because I'd have to take the 6th root of 64, y the 12th to the 6th power, and 64 to the 6th power is massively large. So D is not the right answer. And F would have been okay because I would have taken the 6th root of 2y squared to the 6th power. That's 2 to the 6th, y the 12th, times 2y squared will get me back to that, y the 14th, 128, y the 14th. Okay, so more practice simplifying these roots. Some of you, this is overkill for some of you, so if you have other things you want to do, that's fine, but I would definitely at least try some of these. Make this a little bigger here. I can't make it much bigger. Okay, cube root of 250. So I make my perfect cube list. And 125 is what I need. So I'm going to change that to cube root of 125 times 2 because 125 times 2 does equal 250. The cube root of 125 is 5, so I'm left with 5 cube root of 2. Okay? 50,000, 1 to the 4, so I'm making my perfect fourth list. 1681. 256. 625. Okay, I think that you know what it should be. 10 to the 4th, right, is 10,000. So let's change this to 4th root. 10,000 times 5. What am I going to change x to the 7th to? Well, I need it to be a multiple of 4. So the only thing I could change it to is x to the 4th, x to the 3rd. 10,000 can come out, x to the 4th can come out. I'm left with 10x on the outside after I take the 4th root of x to the 4th. What's left underneath is 5x cubed. And there we have it. Okay, I'm going to jump down here in the essence of time. This will be the, I'm going to go ahead and multiply these first. The cube root of 8 u to the 9th. And this is very helpful because the cube root of 8 is 2. The cube root of u to the 9th is u to the 3rd. 54 can be broken down to, there's that bell, cube root of 27 times 2. X to the 8th, I'm going to change to x to the 5th, x to the 3rd. Why did I choose that combination? Because I need a multiple of 3, and that's not what I'm going to change it to. I'm going to change it to x to the 6th, x squared. Cube root of 27 is 3. Cube root of x to the 6th is x squared. What's left underneath? Cube root of 2x squared. Okay, that's where I'm going to stop today. I will do more of these examples on the board tomorrow or whenever you guys work on this assignment in class. But hopefully you can work through some of those examples on your own. If you have any questions, let me know.